What's going on, everyone? This example is meant to help you with the two-dimensional kinematics assignment. So let's get right to it. It says, during a fireworks display, a shell is shot into the air with an initial speed of 70 meters per second at an angle of 75 degrees above the horizontal, as illustrated below. The fuse is timed to ignite the shell just as it reaches its highest point above the ground. And there's a few questions. There's the diagram right here. And the first thing we have to find is the height at which the shell explodes. And as we can see, let's highlight this one over here. This is important because it says that it ignites when it reaches its highest point above the ground. Let's try that again. Why is this important? Well, when we talked about free fall, just getting something and tossing it up in the air, we said that at the highest point, the velocity was 0. And when we had that type of motion, there was no motion along the x. It was just up and down, right? Y-axis. And when we said the velocity, final velocity is 0 when it reaches its highest point, we were talking about the velocity along the y, final velocity along the y. Okay, so that's why this is important. And before let's write down our given. A good first step, or call it 0 step, I don't care, would be finding the components of the velocity along the x and along the y. Okay, so let's do that. Let's get a green arrow for the vector of velocity at 75 degrees. So there you go. That's pretty good. And I'll place it here. And we know this vector is composed of vectors or components along the x, along the y. It's moving both to the right and up at the same time. So now, let's get the components. So the component along the x looks like this, kind of short. There you go, that's good. Now let's get the component along the y. Gotta move it. There you go. Not perfect, but pretty good. Here is a right angle over here, 90 degrees. So let us get this one going. For this one, let's pick blue. So let me do 90 degrees. There you go. This is V naught. And, well, let's use black, right, because we have these vectors in black. This is velocity, initial velocity along the x, and this is initial velocity along the y. We can use trigonometry because we know this is 75 degrees over here. I'm just going to call it theta. But we know that theta is equal to 75 degrees. And we can find, we can define x and y components based on the initial velocity because we have a right triangle. We can use trigonometry, okay? So we're going to use the opposite side, which is velocity initial along the y. We know that when we use the opposite, we have to use sine. Sine of theta equals opposite divided by hypotenuse. The hypotenuse is the initial velocity. So it'll read like this. Sine of theta is equal to opposite v naught y divided by v naught. We're trying to solve for v naught y, so I will multiply times v naught. Here, v naught is initial velocity. And we have that v naught y equals v naught times the sine of theta based on trig. And we can do the same thing here with the cosine. So let's just do it right here. Cosine of theta equals adjacent, which is v naught x divided by v naught. That is the hypotenuse. Cancel v naught. There you go. And v naught x equals v naught times, no dot, just like that. Whoops, times the cosine of theta. Now these are very important. We'll use them right now, okay? This one and this one. We can find the values. I'm not going to do it just yet. I'm just going to have the variables because I do have theta, 75 degrees, and I have initial velocity, which is 70, okay? Now, let's answer question A. Notice I have the equations from our formula chart here, and it says find the height at which the shell explodes. Okay, so the height, it's just green. We have learned and discussed during class that height for two-dimensional kinematics we define as displacement along the y-axis or just delta y. Okay, so we need to find delta y. Let's list our given, knowing that the unknown is delta y. So okay, there you go. Given. I don't like this one. Given. We have initial velocity along the, well, just initial velocity, right? We don't know what is the initial velocity along the x or along the y yet. We know how to find it, we just don't have the number. So V naught is 70.0 meters per second. That is the velocity, right? Yeah, okay. And then theta is 75 degrees. We have acceleration due to gravity, 9.8 meters per second squared. And we're trying to find delta y, which is our unknown. We have these four. Since we're looking at the y-axis, you can see we have displacement along the y, which is the height, acceleration due to gravity, which is down, that's the vector. So let's find V naught y. So V naught y is V naught times the sine of theta. So V naught y equals V naught, which is 70.0 meters per second times the sine of 75 degrees. Make sure your setup is on degrees, not radians, okay? Look, DEG, degree. So that is 70 for the velocity times the sine of 75. And 67.61, right? Just two significant digits, so 61. So our initial velocity along the y is 67 point, actually just one significant digit, 0.6 meters per second. There you go. Now we need to focus on theta, acceleration due to gravity, delta y, and we have now initial velocity along the y. We don't have an equation that, because look, we don't have time, right? So we could find time, but let's just we can find height without finding time first. We can't do it. And you will not find an equation like that here, well, at least with all these. What I'm going to do is I'm going to use this one, but I'm going to do something. So let's get the blue highlighter. I'm going to use this one. You'll see why. I'm going to use blue so I can use this equation. So I'm going to write it down. It says, so let's write equation. Or equations in plural, right? So we have V final squared equals V naught squared times sine squared theta naught, whoops, minus twice acceleration due to gravity, delta y. Okay. I could use this one, sine of theta, but look, I'm going to show you a different way based on this. So if I write this one like this, v naught sine theta squared, they're the same. Now this theta naught, we don't have to write it down because we have only one angle, okay? So that's okay. Minus 2g delta y. Notice how v naught sine of theta, it's also v naught y. Look at these two. There you go. So then I can say, well, then final velocity along the y squared equals v naught y squared, don't forget about the square, minus 2g delta y. That's ugly. There you go, delta y. And I mean, I could have used this one. I just want you to have this one in your notes, so write it down. And let's solve for delta y, which is very simple, right? I'm gonna need more space. Oh, that was my bad. Okay, so let's solve for delta y. The first thing I'm going to do is subtract v naught y squared. Don't do anything with the squares, okay? You don't have to do anything with the squares. At least not now. So velocity final squared minus velocity initial squared equals negative 2g. Oh, I forgot the y right here. Delta y. I just want delta y, so I will divide by negative 2g. This one cancels. And I'm going to write down my solved equation over here. Delta y is equal to v final y squared minus velocity not y squared divided by negative 2 times acceleration due to gravity. Now you might be asking, well, we don't have the final velocity along the y. But we just said that this one will reach its maximum point, or its maximum height when the velocity along the y goes to 0, because let's say nothing happened, right? The fuse didn't work out. This will just fall following this projectile motion trajectory like this, but it'll change direction over here, which means it'll cease to go up and start to go down because of acceleration due to gravity. So then velocity final along the y is 0 meters per second, meaning we can just cancel this one, and we'll have delta y is equal to negative v naught y squared divided by negative 2g. Now we just substitute. Now be very careful with the negative here. Leave it outside the parentheses is 67.6 meters per second squared divided by negative 2 times 9.8 meters per second squared. So these two negatives are going to cancel. I'm still going to include them so you can see, right? So parentheses, negative, parentheses, 67.6 squared divided by parentheses, negative, parentheses, 2 times 9.8. And the height is 233.15 meters, We're using just 3 numbers for significant digits, as you can see. Well, I mean, I should have 3 or 2. I'm just going to keep 233.1. Or 0.2, let's just round it to 2. I'm not following significant digits. I should, but I'm not doing it. And I'm not going to do it, although you should. Okay? So 233.2 meters. Well, just let's do it 233. Delta y equals 233. I said not point something, just meters. And there you go. Okay, that's how you find the height. Now, let's answer. Oh, I didn't need that much space. So let's answer. This is weird, huh? One more. There you go. Question B. How much time passed between the launch of the shell and the explosion? In other words, find time from release from this point to the highest point. Okay? We already know the height. Now we could use this equation or sorry, I want to erase this. There you go. Let me bring this down so we can see it. We can use a combination of these equations because now we have delta y. However, I want to give you a new one. I'm hoping you guys remember when we derived that equation, which we call the bonus equation. So let me just recall. Bonus equation. It's an ugly B. That's okay. It said delta x equals, I need to move this because I'm using a fraction. Oh, come on. Okay, this isn't going to work. Let's try it again. Delta x equals velocity initial plus velocity final. Oh, just like that. Divided by 2 multiplied by time. Let's try this again. It's an ugly T. That was the bonus equation, right? And back then we had motion in one dimension only. That's it. That's why we only used x. But now we have 2 dimensions and we can actually translate this along the y direction too. Don't forget that time it doesn't care about direction. Time is time. So now we can have this new equation where I'll say delta y. Wait. I'm going to write equation over here, equation. Delta y is, you guessed, v naught along the y plus b final along the y divided by 2 multiplied by time. Oh, that's why this looks weird, because I only used the parentheses for v naught and v final. Something was in clicking. There you go. That's better. And we can use it, and I want you to have it in your notes. Okay? We can derive it using this one over here, but I'm not going to do it. Well, no, using this one, but I'm not going to do it right now. If you want to know, I can show you during tutoring. Anyhow, this is getting long. I mean, the video, so let's continue. Let me move this. And now let's write down the given. Let me change this to black to make some contrast. So given we have, well, we solved for v naught y, which is 67.6 meters per second. We know that b final along the y is 0 because that's when it reaches its maximum height. We know acceleration due to gravity is 9.8 meters per second squared. And we found delta y to be 233 meters. Again, we could use more equations, right? We could use a combination of these, but this is the easier one because, first of all, this is 0. Since this is 0, delta y is simply v naught y divided by 2 multiplied by time. Now we just have to solve for time, isolate time. And this is a fraction, so we have to get rid of it, and you know what to do. You flip it, multiply by the reciprocal, so that'll be, need more space. I hate when this happens. I hate it. So delta y equals v naught y divided by 2 multiplied by time. So I'm going to multiply by the reciprocal, which is 2 divided by v naught y over here as well. This cancels, and we have this over here. So then time is equal to twice delta y divided by v naught y. We'll just substitute down. Time is equal, man, what's wrong with my teeth? Time is equal to twice 233 meters. Well, 2 times 233 divided by v naught y, which is 67.6 meters per second. So I'm going to say 2 times my answer divided by 67.6. I'm just going to use this one over here. 148. And there you go. 6.9 seconds, right? 6.9. We could say 8.9. Yeah, I think we should say 8.9 or yeah, 6.89. So the time is 6.89 seconds. And here we go. Last but not least, what is the horizontal displacement of the shell when it explodes? Horizontal displacement, how far? That is the range, your favorite. So this is talking about the range. Let's use green. And you know the range is delta x. Now, the fact that this is the range does not mean you have to use this equation. You can if you want, right? You have theta, you have the initial. You could. But we can make it simpler. We have this one as an option or this one. Now we care about the x-axis, right? Looking at the range, horizontal displacement. So for the given, then we should write down stuff which pertains to the x-axis. In this case, the only thing we know is the initial velocity along the x, which we can find with the cosine, well, with trig, right? So we know initial velocity along the x is v naught cosine of theta, and we know what theta is. Theta is 75 degrees, and v naught is 70 degrees. I mean 70.0 meters per second. So we can find v naught x. As you can see, it is almost identical to the velocity along the y. Well, I mean, how we find it, we just change the function. Cosine of 75 degrees. So that is 70 times the cosine of 75. 18.11 or 0.12. Significant digits, we set 3, so 18.1. V naught x, oh, what happened? There you go. V naught x equals 18.1 meters per second. We know we're going to ignore a resistance, of course, as we do, meaning it is constant velocity, so the final one will be the same as the initial. There's no change. And of course when it stops, right? But we didn't care about what happens after it stops. Well, it's going to explode, so yeah, it's not moving. So I guess I'm wrong. The final velocity is 0 because it ceases to exist, right? But I'm not going to write that down. We don't need it for now. We want delta x. Well, we have time now, right? Which is 6.89 seconds. And we want delta x. Well, if I focus on these three, again, I could use the range equation. I'm not going to because I don't have to. I could, but at this point I'm tired, and I could do just for fun. You know, like doing problems like this just for fun, but I know you may not be having as much fun as I am. So look, I can use this one. Delta x, v naught x, and time. Simple. So equations. And I don't even have to solve for anything because it's delta x, that is the range, equals v naught x times or multiplied by time. So delta x is 18.1 meters per second times 6.89 seconds. So delta x is, let's see, so I'm going to use my answer, control answer. What happened? Let's try it again. Control answer times 6 point, I'm using this one, 89645, 124.9, 3 significant digits, so 125. So the range is 125. I know my 5s look like an S. Let me fix it before you guys complain. Here you go, that's better. Meters. And there you go. Don't forget, make sure you see, okay, am I going to focus on the x-axis or y-axis, and then split it. Write down the necessary information. Find the most helpful equation and the one that's going to make the mathematics easier. All right, hope this helped. Bye.